Today we will compute a lot of things, and I hope that we will have time at the end of the lecture, and then we will discuss ramified couplings a bit. But I decided to start from the reminder about intersection form on the Picard rule of surface, just because it's a very important notion, and we will constantly use this notion later. So suppose that we have, for simplicity, non-singular complete surface over some base field, then we have Picard group of the surface, just isomorphisms classes of invertible shifts on this non-singular surface. And what is a very important feature of the case of surface is that on this group we have an intersection form, just in this case. So let me remind how we can define this intersection form. So suppose we have two line bundles on this surface, then we define this intersection form in the following way. We just take Euler characteristic of the surface minus Euler characteristic of the dual line bundle minus Euler characteristic of the second line bundle, and then plus Euler characteristic of their tensor products. Okay? Where I remind that this is just an alternating sum of dimensions of the cohomology of this line bundle. This is symmetric bilinear form. Symmetric bilinear form on the Picard group. And in fact, this form has the following properties. So the very first property is about the following thing, that this intersection form corresponds to an intuitive definition of the intersection of two curves. So suppose that L, почему так жирно? Suppose that, ладно, лучше не стало. These two line bundles corresponds to two curves. Кто-нибудь может мне помочь? Как сделать так, чтобы это было не так жирно? Или это не важно? И так все видно. Ладно. Сейчас. Да я пыталась уже. Тоже сделала. Вот так. Ладно. Я знала, что с этой доской будут проблемы. Are two curves on C intersecting. So suppose that these two line bundles corresponds to two effective divisors. So two curves on our surface intersecting in only finitely many points. X1 and so on, xn. Then this intersection is just the sum of the following dimensions over base fields of the following vector spaces. We just take local rings on S. On S in Xi, and then we take F Xi G Xi, where F, Xi, and G, Xi are local equations, of C1 and C2. Okay. So why this this intersection form? So this is something that we need to prove, but I decided not to give an explicit proof of this fact, that if we define intersection form in such a way, and if we take two effective divisors, then we obtain an intuitive notion of the intersection. I'm not going to prove this, but maybe I need to give some comments why this corresponds to an intuitive definition. So of course, intuitive definition of the intersection of two curves, this is, so if we have two curves, we have some points in their intersection, and we should take these points with multiplicities. So for example, when this dimension is equal to 1 in what points? It's equal to 1 exactly when C1 and C2 intersects transversally. Because in this case, so in this point, so dimension over K of S X1 or Xi is equal to 1, even only if C1 and C2 intersect transversally. Because this means that it's equal to 1 when this ideal generates the maximal ideal of the point x1. So f and g gives local coordinates around the point xi. So So we have some local coordinates in this point, and this intersection is transverse. Okay. So and it's easy to see that indeed. In general case, we will have these points just with multiplicities. So the strange formula that was written here before corresponds to an intuitive notion of the intersection. So what is the next property? So for non-singular irreducible curve. C inside surface and O line bundles in the Picaric group of this smooth surface, we have the following. If we take the corresponding to this curve line bundle and intersect it with the line bundle L, then we will obtain degree of the line bundle L restricted to this curve. Okay? How we can prove this? The proof is very easy, so I decided to do it here. So we have two exact sequences. First is for the ideal shift of OC, then to OS, then maps to OC. And then we can twist this by the line bundle L. And from this exact sequences, we immediately get the relations of the corresponding Euler characteristics. Minus Euler characteristic of L minus 2 minus C is equal to okay, is equal to this. And now what does this mean? If we so if we now intersect OC with L, then using this formula and just the definition of this intersection, what we will get? It's just a computation. Нужно просто подставить и получить. So what we will get?
The difference.
The difference. So the difference of what to what?
Of C and T of minus 1.
So this is just by definition. And now, what is this?
What?
What is this? What is this difference? Not that here we have a curve C. What is it? What is this?
1 minus the degrees.
This is just a minus degree of L minus 1 restricted to C. Do you know why? Yes, this is just Riemann-Roch theorem for curves. So, and this is, and this is, of course, degree of L restricted to C, right? So we get this formula, and everyone knows what is a Riemann-Roch theorem for curves. I suppose so, right? Great. This was the first property, and now let me see the third. This was the second property, and now let me state the third one. This is the Riemann-Roch theorem for line bundles on surfaces. So the statement is the following: that the Euler characteristic of a line bundle on the surface is equal to the Euler characteristic of the structure shape plus the intersection of L with L minus the intersection of L with the canonical bundle of this surface. For curves, the classical Riemann-Roch theorem for curves also the statement also relates the Euler characteristic of a line bundle on a curve with the Euler characteristic of the structure shape of a curve. And here, for curves, we have degree of the corresponding divisor, and for surface, it has a following form. Of course, there is a much more general theorem of Riemann-Roch perpendicular, you know, but here it has a very simple form. It's much easier to remember. Before I decided also to give a proof of this fact. If it's okay if I give a proof, because I think that the intersection form on the Picard group is very important thing. We will constantly use it later, so maybe we need to have some experience of working with this thing. Okay, and so before I will give a proof, let me remind also the so-called Serre duality. It's a very important duality that is constantly used in algebraic geometry. So, Serre duality. This is a very general statement for any smooth proper variety of dimension n and for all vector bundles E on X, we have the following isomorphism. If we take cohomologies x e, then it is isomorphic to n minus I cohomologies on x of the dual vector bundle twisted by the canonical class of x. Okay? It's
Maybe dual something.
here is dual, right? So this is the statement of the third duality, and we will use it many times. And now let me give proof of the Riemann-Roch theorem. First, let us compute what we will obtain if we will intersect these two line bundles. The first line bundle is the inverse to L, and the second is L times S minus 1. So what is just by definition? What is this? Just definition.
Here of all
Then minus what?
here of A minus here of L times 1 times
And then
and that was
Now we're using the third duality. What is this? So what tell us the third duality in the case of the surface? If we have a surface, yes. What this isomorphism tells us about earlier characteristic of a line bundle on the surface.
And then it's just
Key of L is equal to key of L inverse. That's the canonical shift.
So I will write it here. On S, Euler characteristic of L is equal to, right? So what is this? What is this? So what is this? Just by third duality.
kind of OS.
And what is this?
KFL.
Right? So now, what we get? We get that L minus 1, L or S minus 2 is equal just to 2 x minus 6L. Right? So, and we immediately obtain the statement of the Riemann. Okay? Just by, because this form is by uniform. Okay? And now, let me present some computations in the case when we work with a K3 surface. So now suppose that it's this was just a reminder about the intersection form on any surface, on any smooth surface, and its general properties. So the Riemann-Roch theorem works for any smooth surface, not just for K3 surfaces. And the other two properties also work for any surface. And now, what all this gives us in the case when X is a K3 surface. So first of all, just by definition, we have that this is equal to 1. And this is equal to 0. So here duality on the K3 surface tell us that is isomorphic to what? Mm-hmm. Mm-hmm. And this means that H2 of X or X is also equal to 1. And now we obtain from this immediately that the Euler characteristic of the structure field of X is equal to 2. Okay? Sorry, I know that all this is very simple, but maybe for those one who never seen before computations by Riemann-Roch, maybe it's important to explain all these things. So, okay, we get this, and from this, for example, we can immediately get that we that for a separately closed field, if we will consider K3 surfaces over separately closed field, then there will be no unramified covers of K3 surfaces. Okay, why this is so? So from this we get that there are no etal covers of X of finite degree. Of finite degree over separately closed field.
What is separately closed field?
Сепаративно замкнутое поле. Это значит, что нет правых корней. Все регулярно. So maybe I need to give some comments why we need here separately closed, because if the ground base field is not separately closed, we always will have unramified covers that corresponds to separate closure. So I'm not going to discuss this in details, but for those one, if someone is interested in finite characteristic, this is just some comment. Okay, so for over non-separately closed field, we always have etal cover of finite degree. non-trivial Ital cover. Okay, so we need to ask the ground field to be separately closed. And now, what is the proof of this fact? Suppose that we have an Ital, everyone knows what is Ital cover. This is just unramified, unbranched cover. Okay, maybe we will discuss in the end of the lecture this. So suppose that this is irreducible cover of degree D. Then what will be the canonical bundle of X tilde?
Just a global bundle.
Yes, and what is this for a K3 surface?
The structure sheet.
Mhm. This is the first thing. And now, what is the Euler characteristic of the structure sheaf of X tilde? Or an unramified cover of degree D. We discussed last time what will be a push forward of OX on X. Yes, this will be just D copies of O of structure sheet. So this means that the Euler characteristic of this thing will be what?
0.
No.
3 times.
And what is this? We just computed it.
2.
Right. So when we have unramified cover of degree D, we have this equality, right? Just because we can consider push forward of this shape, and we will see that Euler characteristic will be D times Euler characteristic of the base. Okay, and now how we can prove that D should be equal to 1. So the global sections of X will be by cell duality. This will be what? Of what?
It's
And this is equal to 1. And in fact, here we use that field. We use that the field should be separately closed, exactly in this thing, because otherwise, if the field is not separately closed, we can have here something bigger than 1. Okay. But here, in this case, we have this equality. Okay, but this, what does this mean? This means that 2 minus x is equal to 2d. And this means that d should be 1. Okay? So you see from the computation of Euler characteristic of the structure sheaf of the of a K3 surface, we immediately get, in some sense, a non-trivial result that we don't have unramified covers of finite degree. So this means that so-called algebraic or Ital fundamental group is trivial. And over the complex numbers, this means that just the classical fundamental group of X doesn't have finite quotients. This, by the way, relates to your question that we didn't prove that this is trivial because here we consider just finite covers, and maybe we will have some some infinite cover. So we need to. In fact, this will be trivial, but it's a more difficult result than the triviality of the algebraic fundamental group. Here we just proved that there are no finite quotients in the fundamental group over C. Okay? Okay. This was the first computations with K3 surfaces, and now let me state what is the Riemann-Roch formula for a line bundle on a K3 surface. So Riemann-Roch for surfaces what is this? Plus?
Plus
L squared divided by
So in the case of K3 surface, it has a very simple form. Now let me also state how we can. Let me also formulate how we can play with this formula. So first of all, let me remind that for a line bundle L on a projective scheme, or in the analytic case just on a compact variety scheme, H0 X L is not trivial, and H0 of X L dual is non-trivial if and only if what?
No, it's just the structure shape.
L is trivial. Note that, of course, we don't have this statement in the case of affine manifold, right? So here we should ask projectivity. Okay?
Proper is not enough.
Proper is enough. So what we want is that to prove this statement, it's enough that the global sections will be just one-dimensional.
Yes.
So now, how we can use this observation? To simplify Riemann-Roch formula. Okay, first of all, by sheer duality, H2 XL is isomorphic to H0 X L to L. So Riemann-Roch for a non-trivial line bundle, non-trivial line bundle on a K3 surface. Surface will have one of the two forms depending on what are non-trivial global sections of L or of L dual. So this is just an explanation to simplify your life later, how we can compute all these things faster. So this gives you this thing. Or L dual. And for trivial line bundle, of course, this is a trivial one. Okay? So, and also let me just mention how, let me also state what we will obtain for an ample line bundles or in the, of course, we have ample line bundles just for projective K3 surfaces. So this statement will be just for projective K3 surfaces, but we will mostly interested in the in projective K3 surfaces. So maybe it's important to state this theorem just because I also want to formulate another important computational tool in algebraic geometry that is so-called Kadaira vanishing theorem. Okay. So let me first Kadaira stated. It's very famous, and in fact it's a difficult theorem, so it's very difficult to prove, but it's very easy to use and very important to use sometimes. Kadaira vanishing theorem. So first, this statement holds just for field of characteristic 0 for K of is 0, and in fact in positive characteristic it fails. There are examples when it doesn't work. So, and we suppose that M is smooth, projective K-scheme of dimension n, and L is an ample line bundle. Ample line bundle on M. So this means that it's the tensor product of this line bundle, some tensor power of this line bundle will gives you an embedding in the projective space. We have the following vanishing. Q cohomologies of M, L, O times scalar differentials of M over the base fields is equal to 0 for P plus Q greater than the dimension of the variety. Okay? And now for K3 surfaces, this tells you what? for a projective, because we also define the projective. This tells you what about Q homologies of an ample line bundle.
It's zero if
Greater than 0. Okay? And now also let me briefly mention that so I said you that Kadeira vanishing theorem fails in positive characteristic. But in fact for K3 surfaces it works in positive characteristic. So for K3 surfaces we can use this theorem. The proof is not very difficult. Maybe we will discuss it at some point. A deeper reason for this theorem to hold in this case is that K3 surface do lift in characteristic 0. Okay? But this one we will not discuss because this is the Ligney-Luzy result and I'm not going to discuss it. But there is a direct geometric proof of this fact in the case of K3 surface. Maybe we will discuss it, but not. Okay, so in particular, this will hold for an ample line bundles on a K3 surface in a positive characteristic too. Okay? For an algebraic K3 surfaces. Okay, now from this we immediately update that Riemann-Roch theorem for an ample line bundle L on X tells you what?
H0 of A equals to 2 plus A squared.
So for an ample line bundle, we immediately obtain global sections from the corresponding intersection okay, on a K3 surface, and even in positive characteristic. Okay. And also, let me present a very general James formula on any smooth surface, and then we will discuss what gives us this genus formula in the case of K3 surface. And then we will discuss coverings. So the genus formula so suppose we have an irreducible curve on a surface S, then the genus of this curve is equal to 1 plus the following sum: C plus C okay. So and let me remind that the genus of the curve, this is just the dimension of the first cohomologies of its structure sheet. Okay, and now how we can prove this, because the proof is also very elementary, so I decided to do it. Using Riemann-Roch wrong, of course. And also I would like to show how we can use Riemann roll. Something. So we have this, it's, our favorite exact sequence on S. So the Euler characteristic of OC. This is just what in terms of the genus? Diffusion.
2 minus.
Wait.
This is just 1 minus G.
Here, yes, I mean on C, but 1 minus genus. Because this is curve, this is not surface. Okay? And from this exact sequence, this is what? This is Euler characteristic of OC minus Euler characteristic of the thing. And now, just by Riemann roll, this is plus C S. So this is just this. And we immediately obtain our formula, right? So we obtain this formula. And now let me state the following lemma on the K3 surface. We will use this lemma later. So let X be a K3 surface and C in our K3 surface is a smooth curve of genus G. Then C times C is just 2G minus 2. Maybe I will usually denote the intersection of C with itself by C squared. This is the first thing. And the second thing is that global sections of C of the structure sheaf is just. So maybe here I should write. Сейчас. Of OC. So proof. So how we can? So first of all, how we obtain this thing? No.
Immediately from Schluss formula.
Yes. No, adjunction formula. Okay, it's genus.
Previous step,
Yes. Genus formula implies you this. And now, how we can prove the second statement? So we from the what is this one? Very new, right? So this means that to show the statement, we just need to show that the first homologies near
Там можно отменить. Там можно отменить.
да?
Да. Вот несколько раз.
Ага, окей. А теперь... Okay, this means that it's enough to prove the vanishing of this first homology, right? And using the third duality, this is equivalent to what?
First homology of on X of minus C.
Yes, and how we can prove this vanishing? We can use our favorite exact
Sequence, yeah.
Yes. Minus C. Or X. And also this exact sequence and the long exact sequence of the homologies will immediately imply this vanishing. Okay? I'm sorry, but I decided to explain all these things. Great. We will use this thing next time, I suppose. And now let me. Last time I said that maybe we need to discuss. We decided to discuss coverings. So now let me state some results about them. So coverings. It's not so. It is not directly related to the K3 surfaces, but as far as I understand, most of you didn't remember what is the formula for a canonical bundle of a branched cover, as far as I understand. So,
Yeah. Also, I didn't understand why the characteristic of structure sheaf of cell covers two times characteristic of the space. I can also ask this after.
okay. Coverings. Okay, so first, what is this? Last time, when I give you an algebraic picture, I give a definition of a cyclic cover. And what is the cover in a more general sense? So, in an algebraic word, I would say that X to Y is called, this is a cover. If so, this is cover when phi is finite, surjective, morphism, of normal schemes. Why normal? Because, for example, when we take a normalization of a nodal curve, we will, you know this geometric picture, right? For us, this is not a cover, this normalization. So here is why we asked these two schemes to be normal. Okay, because in a cover, okay, I will explain in a minute what I mean. So this is not a cover in this sense. Okay, and maybe for simplicity, we will discuss smooth or regular schemes. Okay, for simplicity. Because for non-smooth schemes, we just ignore this. When we prove all these formulas, we just ignore this non-smooth locus. Smooth for simplicity. Okay, and maybe let me also state that analytically, I would say that this is a finite morphism. Because when we discussed Kummer surfaces, we also discussed an analytic case of a non-projective torus. Finite surjective. Finite surjective proper holomorphic map of normal to, it's important, of normal complex manifolds. Okay? Now, what is the degree of the corresponding of this thing, of this covering? Degree 1 is just degree of an extension of fields of the corresponding properties. Okay, and for
what
in
is
this
by pi upper scalar pullback of function fields here?
just because I don't know how to. What is this standard notation? No?
Like for pullback of the
Okay.
observer shift should be self, so maybe. Yes.
Or so this is just in this case when we have a finite extension, this degree is finite. Okay. So, and what is the statement? In fact, it's not trivial. You should say something, but it's not difficult. That in this setting of finite subjective morphism of normal or for simplicity smooth schemes, the number of pre-images of input Y inside Y is less or equal to degree of pi. So here you see we are over the nodal point, we have 2 points, right? And here in this setting it's not allowed. Okay, we always the number of pre-images is always less or equal to degree of pi. Okay, and we will say that the point is range point if this number of pre-images is strictly less than degree. So I prefer to think about all these things geometrically. This means that here over any point we have a finite number of points, and they cannot just disappear in some fibers, but they can glue in something. Okay, so they cannot disappear; they can glue. And the points where this gluing happens are called branch points. Okay, and now what is the ramification divisor? Let me first state it in the following way, and then I will explain what does it mean. So this is 0. So intuitively, it is clear what is this divisor parameterize. This divisor parameterize the points inside X where the morphism pi isn't smooth. Okay? So when some points are glued together, in these points, the corresponding morphism is not smooth. And the ramification divisor here on X, this is a divisor that parameterizes these points. Parameterizes these points. Okay, ramification divisor is 0. Divisor of the canonical section. I will explain everything by a prostar before it's okay if I will sometimes write k, and if I will sometimes write omega. This is always a canonical bundle. I suppose that everyone knows this. The formula that we discussed last time from this definition is just follows just from this definition. So that kx we have pullback of here right pullback of the canonical sheaf of y times ramification divisor. So let me now state this formula maybe in some sense analytically. So suppose we have a point x inside x, and suppose that y1, yn are local coordinates, maybe algebraic coordinates of yx in y. Then near this point x, ramification, we define the ramification divisor R to be the divisor that corresponds to the following form of higher degree. So it's easy to see that this definition doesn't depend on the choice of the local coordinates, because if we change local coordinates, then the corresponding divisor will change by something that is unit in the local sheaf of the corresponding point. And now let me give a more explicit definition explicitly. If x are local coordinates of the point x, then mu x, the ramification divisor is just divisor of the Jacobian. Determinant of P opposite star P. So that the support of this divisor is just a set of points where the morphism is not smooth. So what all this mean informally? So we have a map of two varieties of dimension n. So analytically, and in fact in algebraic theory, we can also give all explicit definitions. We have a map, but okay, roughly speaking, we have a map of tangent spaces in each point. In what means that the corresponding morphism is smooth in some point. This means that we have an isomorphisms of the corresponding tangent bundles, tangent spaces, yes? And what does it mean when the corresponding morphism has a, that the point is not smooth for the corresponding morphisms? This means that we that the corresponding map of tangent bundles is not isomorphisms. So now, and R ramification divisor is something that parameterizes these points. So in fact, from this, we immediately get this formula, right? Just because, so here in local coordinates, this is a way how we can understand when the corresponding map of tangent bundles is not isomorphisms. So this is exactly zeros of the corresponding determinant, right? And from this, we immediately get this formula, right? And so, we still have 5 points, 5 minutes. Okay, and last time we discussed, I will write this just so-called cyclic covers, and maybe in 5 minutes I'm not going. Maybe it's better to start the next lecture from the reminder of what was the cyclic cover and how we can rewrite this formula in this case in terms of the vector bundle on Y, because I also wrote this formula and there was some questions. What is a so I mean here we have branch points in Y, and here we have a ramification divisor here. And when we have cyclic cover, we can write the correspond. Okay, maybe I will write it down now, and we will discuss it later. Okay, for cyclic cover, here I will X. Okay, X is just the pullback of the Ln minus 1, where when the corresponding cyclic cover has was branched in divisor B such that the corresponding line bundle was tensor power of the line bundle. So this is an n root of the line bundle that that is given by an effective divisor. Okay, and maybe next time I will. Last time I discussed what an algebraic picture. Next time I will explain a geometric picture of how we can define using this data a corresponding cyclic cover, and how we can obtain from this formula this. But for this we need to define ramification degree, and maybe I need more than 2 minutes for this. Okay, or we can just ignore all these things and what you prefer.
Next time, please.
Okay.